The last topic I want to talk about in this chapter is the Heisenberg uncertainty principle. And it's possibly one of the strangest ideas that we will learn about in this entire semester, possibly the entire year. To set it up, let's go back to a situation we discussed in an earlier part of this chapter, and that is the diffraction of particles acting like waves as they pass through a small circular opening. So we saw this pattern before. We see these distinctive rings that are the diffraction pattern from the matter waves passing through this opening. Notice that in each of these cases we get a bright ring in the middle here. We get a bright spot in the middle. So from a sort of a side view, this schematic looks like this. We've got some width for our opening here, and then we have some width down here where that pattern has this nice bright spot in the center. We can't predict with certainty where an electron will hit, but most of them land within this first bright spot here. In order to do that, they must have some velocity in the sort of sideways or in the x direction here. Right? We know they're moving in the y direction because they make it from the slit down to the screen. But in order to have this spread here, some of them must have some velocity in the x direction. And it turns out that the narrower that slit is, this slit here, the narrower this slit is, the wider this bright spot is. That's a little bit counterintuitive, but it's exactly the same thing we saw when we were talking about diffraction of light. And the same thing happens with sound waves as well. The narrower the slit, the wider the diffraction pattern. So we can think about this as, if we constrain the particles in the x direction, then we know less about their velocity in the x direction. If we know more about exactly where the particles are by forcing them through a narrower opening, then we know less about their velocity in that direction. And therefore, some of them might have a large velocity in the x direction and could end up way over here. This is the basis of the uncertainty principle. It says that we can never ever know exactly where a particle is and exactly how fast it's moving at the same time. Never ever. Like, you can never know precisely an object's position and precisely its velocity. It's a very, very surprising conclusion. Mathematically, it looks like this. It says the uncertainty delta x in its position. Well, uncertainty, that's not actually something we're going to define mathematically here. In this context, we'll take it to mean, what is the error in our measurement for x? In other words, how well do we know the location if we're talking about delta x? And for delta p, that's its momentum. So how well do we know its momentum? Given that we almost always know exactly what a particle's mass is, the uncertainty in momentum ends up being an uncertainty in velocity, since we generally know exactly what its mass is. And so what Heisenberg's uncertainty principle says is that there is a lower limit on how well we can know the position times the momentum. In other words, if we know one of these things really well, then we know very little about the other. In other words, if we know exactly where the particle is, then we know nothing about its momentum. Alternatively, if we know exactly what its momentum is, then we know nothing about where it is. Going back to this diffraction pattern, by making the slit smaller, we know better and better exactly where those electrons are in the x direction, because they have to pass through this narrow slit. So we're constraining them in the x direction, so we know better exactly where they are. That means we know less about their velocity. That means we can't know exactly whether they're going 0 velocity in the x direction or some larger value. We tend to get a larger spread. This is a lower limit. And h is a very small number, right? 6.6 times 10 to the negative 34 joules times seconds. So it's a very small number. So for normal, everyday sized objects, we just never notice this. But for very small objects, this effect can be very significant. In fact, Heisenberg's uncertainty principle is putting a limit on how small manufacturers can make computer chips. Because in order to make computer chips smaller and smaller and smaller, they need to constrain electrons to smaller and smaller channels. at some point, you might get electrons jumping from one channel to the next. Why? Because if I constrain it, try and put it in a smaller and smaller box, I know less and less about its velocity. So maybe I know that it's right here right now, but I won't know where it is in just a minute. It might be over here in this other channel where I didn't want it. And so computer manufacturers are actually bumping up against this right now. In fact, for a number of years, computer chip manufacturers have been saying, we're approaching the limits set by the Heisenberg uncertainty principle of how small we can make these computer chips. Now, they kind of keep finding ways around it, but that's where we're headed. And to be clear, the Heisenberg uncertainty principle says we can never know exactly where the object is and exactly how fast it's going. And this is not just because we don't have good enough equipment. Like this, as far as we know, is a physical principle that the very best equipment in the world will not be able to overcome. So as far as we know, the modern interpretation of this is that this is a literal law of physics, and that nobody will invent a device that will be able to simultaneously measure an object's position and an object's velocity at the same time. And, you know, it was in 1927 that Heisenberg proposed this. And over time, our understanding of it has evolved, but we're still pretty convinced that it is a true law of physics, as surprising as it is. So what range of velocities might an electron have if it was confined to a 0.3 nanometer wide region, which is about the size of an atom? Okay, well, let's just start with the uncertainty principle right here. We're going to start with this. Now, we're talking about an electron, and so we know the mass. So any uncertainty we have in the momentum is actually in the velocity. So let's rewrite that. And I'm looking for a range of velocities, so we'll solve for delta V. Okay, so let's go ahead and plug in our numbers. This is okay, so now I've plugged in my numbers, and all I really need to do now is run my calculator. And I get, oh, this should be, okay, so that's our error in velocity, right? But remember that velocity is a vector. And so that includes direction. And we don't know, it's in a box, so we have a one-dimensional problem. But we don't know whether the particle is going that way, or stopped. We have no idea. If our uncertainty in x is 2 times 10 to the 5th meters per second, well, we really need to center this on 0, because we don't know if it's going that way or that way. Therefore, the range of velocities that we might see would be from -1 times 10 to the 5th meters per second. It's definitely going to be bigger than that. And definitely going to be less than, or equal to, I suppose, 1 times 10 to the 5th meters per second. So, there we go. This is our range of possible velocity. And notice that 10 to the 5th is a very large velocity. So, we really have no clue about this electron. It could be going really fast that way, could be going really fast that way, could be stopped. We just really don't know. So an electron, of course, has an impossibly small mass. And we're confining it to a 0.3 nanometer region. So this is an impossibly small region of space and a particle with an impossibly small mass. How does that compare with a very, very small object? This might be the smallest object that a human could interact with. A 1.0 micrometer diameter dust particle. And to remind you, a micrometer is 10 to the -6th meters. So that's 1/1000th of a millimeter. So very small, but nothing like the size of, nothing like 0.3 nanometers, not nearly that small. So this is a dust particle with a mass of about 10 to the negative 15th kilograms. And we confined this to a 5 micrometer long box. What can we say about this? Can we say with certainty if the particle is at rest or not? Or if not, what range of velocities are likely to be found? Let's check it out. So for our dust particle, we're still going to use Heisenberg's uncertainty principle. Again, we're saying we know the mass pretty well. We're interested in the range of velocities. So we've done our algebra to find our velocity. And now we can just plug in our numbers. It's basically the same idea, but with some slightly different numbers. Let's just see what we get. So here I've plugged in my numbers. Again, h, 6.67 times 10 to the negative 34th joule seconds, divided by 4 pi. The mass is 10 to the negative 15th kilograms. And this is the size of my box. So when I do my math here, what do I end up getting? Well, I end up getting 1 times 10 to the negative 14th. Once again, like before, we don't know whether it's going that way or that way. So we're going to center this uncertainty on 0, which means that it could be anywhere from negative 5 times 10 to the negative 15th. I'm sorry, this is meters per second. It's definitely bigger than that. And less than 5 times 10 to the negative 15th. Well, the question is, all right, here's our answer. The question is, can we say for certain if it's at rest? Well, I guess technically no. But, an atom is something like 10 to the negative 10th meters. So this thing is going to take 100,000 seconds to travel the distance of an atom. Oh gosh, 100,000 seconds. That's like 27 hours. That's more than a day to travel the width of an atom. This thing stopped. We can definitely say it stopped. So again, much like with the watermelon and the de Broglie wavelength that we calculated, we just don't notice this if we're talking about anything even approaching a human-sized object. I mean, this dust particle is probably the absolute smallest thing that a human could interact with without some sort of high-tech device. And even for this tiny, tiny particle with a mass of 10 to the negative 15th kilograms, the uncertainty principle really just doesn't have much of an effect. Again, it is a quantum mechanical idea, and it really comes into play when we're talking about the very, very tiny, when we're talking about atoms and subatomic particles in molecules. And again, this is real stuff, right? In fact, a scanning tunneling microscope is, you probably don't have one in your house, but this is fairly common technology these days. And this uses the idea of the Heisenberg uncertainty principle. A scanning tunneling microscope, it doesn't work like other microscopes, but it builds up an image of a solid surface by scanning a probe near that surface. And then that probe can tell how far away the surface is. How does it tell how far away the surface is? Well, what you do is you put a bias between a probe tip and the sample that you're talking about. And there's going to be a gap here, something like 1/2 of a nanometer. So a very, very small gap. And then what we can do is we put a little voltage on here. That's what I meant when I said put a bias on here. So we put a little voltage on here. And notice that if we make this probe tip slightly positive compared to the sample, there's going to be a little bit, electrons are going to kind of want to jump up here. But guess what? They just can't. There's this gap of 0.5 nanometers. And so electrons just can't cross their gap. This is just not a complete circuit. Like we learned about in our circuits chapter, right? We can't get a flow of electrons through here. because there's a gap right here. We just don't have this complete loop. And that's the end of the story if classical physics was the end of the story. But classical physics is not the end of the story. In fact, the electrons in here, in this sample, well, we know where they are. They're in the sample. That means that we don't know that much about their velocities. If we confine them to the sample, for sure, they're definitely in the sample, then that means they could have a wide range of velocities. The electrons could jump this gap, and this is called tunneling. Why? Because classically, these electrons don't have enough energy to get across this gap. But quantum mechanically, they do. There is a small probability that they will end up over here. Why? Well, we know quite a lot about their velocity. They're stuck here in this sample. Therefore, we don't know that much about where their position is. They could spontaneously end up here on the probe tip. That's really what happens. And if they are, then the current, then it will create a current here, which is read by the current monitor, and the imaging system says, hey, if I'm getting a larger current, then my probe tip is a little bit closer to the sample, and if I get a smaller current, then my probe tip is a little bit farther from the sample. And so you've probably seen some images like this. This is a scanning tunneling microscope image of graphite, and here we see individual carbon atoms. Each corner here is a carbon atom, and this is a lattice of carbon atoms on the surface of some graphite. And so even though we can't create an image of an atom, right? We can't create an image of an atom because atoms are much, much smaller than the wavelength of light. So diffraction effects make it so that there's zero chance that we'll be able to use light to take a picture of an atom. They're even so small that diffraction effects make it so you can't use an electron microscope to see an atom. But what we can do is use a scanning tunneling microscope in order to, it's not quite a picture, but we can see where the atoms are by the increased probability of an electron tunneling into the probe tip. Here is a nice picture of DNA. I think this picture is really cool. You really can start to see that double helix structure in this DNA molecule. And again, this was made with a scanning tunneling microscope. So lastly, how are we going to interpret this? Well, in classical physics, and what I would say our common sense is prepared for, things are either waves or particles. We either know right where they are, or they've got no position at all. They're either spread out, or we know where they are. But that's just not how it works on the microscopic level. So maybe we think about them as a wave sometimes and a particle sometimes. Well, I just really don't think that's the most profitable way to think of it. To me, the best way to think about it is it's neither a wave nor a particle. It's just a whole new thing that our brains are not quite prepared to handle, but if we think about it enough, we'll get used to it. They're just sort of wavy, particle-y kind of things. And these distinction of wave versus particle, it's just too constraining. There's just there's a whole bunch of space in between those two ideas. And yeah, there you go.